Hi, hello, namaste. Good evening, everyone. Welcome to our session on satellite communications. I congratulate all the participants being very active in our course right from day 1 to day 24. We had completed nearly 10 different types of sessions, live talks as well as video lectures on this one. And in this week, we are going to have a summarized activity on assignments, as well as in this session we are going to talk on satellite uplink and downlink design constraints. In that, there are several topics to discuss. Among them, as it is a live session, to a maximum we might cover 3 different topics today. The introduction to the considerations how to design satellite uplink and downlink. Second one is how a general, or to say basic, transmission formula is there between one source to the destination, that topic. And next one is the calculations, signal to noise ratio calculations we are going to determine. These 3 topics we may complete today in this live session, and the same sessions will follow for the rest of the days. And on 30th of this month, we are supposed to have a certificate ceremony, and this course is organized jointly by Institution of Engineers Kadapa chapter and Kasigari Institute of Technical Education, KITE, KITE. And I am very happy and glad to invite all of you to this particular session today. Let's start the session on satellite communications, very particularly satellite link design concepts. So this is what we are going to discuss, that is about satellite link design concepts. Here in this session, that means in this course, we are supposed to have a discussion on these many number of topics, like the basic transmission theory. So how the transmission is taking place from source to the destination, and in that one, the antennas that are used for transmitter as well as receiver, their directivity, their gain, and what is the transmitted power, what is the received power, those things we are going to define in the basic transmission theory concept later. And this entire system, satellite communication system, finds what is a different various kinds of powers, like transmitting power, receiving power, and they travel for longer distances. Therefore, some noise will be introduced in the communication system, the two satellite communication system. So how that system is affected due to noise, and what is that noise temperature, and the ratio of G, gain to temperature ratio, is going to be defined here. Then we design the downlink and uplinks. So design of downlink, and next one is design of uplink, and finally design of satellite link for a specified, for a particular carrier to noise ratio with some example. Then one type of technique that is implemented in satellite communication is multiple access techniques. Among them, we study about a TDMA, time division multiple access technique, and its TDMA frame structure. And then finally we will define about TDMA onboard processing technique. Likewise, these were the contents we are supposed to define in this week about satellite link design concepts. So here in this session today we might complete the first 3 topics, like introduction to satellite link design, basic theory transmission, and next one is system noise temperature and G by T ratio concepts. Up to here, the 3 topics we are supposed to complete by today's topic. So let us define. See, as we know that in our previous sessions we have discussed that satellite is an eye in the sky. It receives the information from the earth station, process the data, and retransmits the signal to the ground station. So it is a bridge between one point to another point on the globe. Since for a shorter distance it is okay, communication can be established easily, but whereas for longer distances, due to the curvature of the earth, obstacles, attenuations, and many other things, the information may not transfer for longer distances. It finds its limitations. So now in order to transmit the information for longer distances, satellite is a medium. So from ground station, the signal will pass on to the satellite. It receives re-radiates the signal to the another ground station or to the same ground station. So here the signal that is transmitted from ground station to the satellite is called uplink, and that is pushed down to the ground station again is called downlink. So this link design we are going to define in these concepts. So very first, design of such a satellite communication system is very important, and it is not a simple task. As we said in a single sentence, it is not that much simple task. It is a complex process. For that complex process, we, the electronics and communication engineers, satellite engineers, will take up so many calculations with a lot of design procedure. They design in order to provide better performance. A better performance is to be given by the satellite. So for that particular objective, that too, the cost should be at acceptable range only. If the cost is very high and the communication system is established, then it may not be helpful for all the people. So cost should be minimum and the design should be simpler. Though it is a complex process, it should be a simpler one, and the performance level should be at a greater level. So with these constraints, in our view, we have to design a satellite. So very particularly, we know that the moment when we launch the satellite through a launching vehicle, that satellite will be carried by launch vehicle and placed in orbit. And once the satellite is placed in orbit, it revolves, to say it rotates in that particular path. That path is called satellite orbit. We know that there are several types of orbits: low Earth orbit, medium Earth orbit, and GEO, geostationary Earth orbit. Likewise, different types of orbits we have defined, and each orbit has its own applications and constraints. So in this constraint, the very particular factor in designing the uplink and downlink is particularly the weighing factor. That is, the weight is the most critical factor in design of any satellite. As the size, the weight of the satellite increases, if it is heavier, then the cost incurred even in launching the satellite and also to maintain that satellite in the orbit also increases. This is the basic thing. So therefore, the capital cost should be reduced. When the capital cost is reduced and maintenance cost is reduced, then automatically we can provide the communication, that means the services and the performance of that system for better levels, and for many people particularly. So to do so, the overall design of a satellite is a complex thing, and we have to take so many critical steps and design procedures, because if once it gets a fail during the time of launch, or even if when it is lifted into the orbit, if anything failure happens, mismatching happens, then automatically the entire work for years together will be of waste. Therefore, very careful observations, calculations, design and execution is required in making the satellites. Very specifically, a satellite carries some antennas. So as the satellite is there in the space segment, it receives signal from the ground segment. Since an antenna should receive that signal, so the size of the antenna now is a big question. The size of the antennas which has been used here, and also the components that are placed in a satellite, all should be carried by a launching vehicle. Therefore, there is a limitation to a maximum. The dimensions of those components in the spacecraft should be less than 3.5 meters only. So in that just 3.5 meters less than diameter space, we have to place the satellite, and all the components needs to be lifted into the orbit. So once the satellite is launched into the orbit, very particularly the important element that is there in satellite communication is antennas. So the size of the antenna, weight of the antenna, the shape of the antenna, everything impacts. The radiation pattern of an antenna also impacts. Gain of an antenna, directivity of an antenna, the temperature produced there, radiation resistance, all the antenna parameters plays vital role in this communication establishment from one point to another point using satellite. Therefore, two important factors are to be taken into consideration. They are the number and the output power of the transponders. How many number of transponders are used here, and what is the output power that is incurred by the transponder. And next one is, once the satellite is placed in the orbit, it has to maintain in that orbit. To maintain the satellite in that station keeping position, it uses additional fuel. So weight of the station keeping fuel is also important factor in designing the satellite. So apart from this, the other important thing is we estimate a satellite to function for 10 to 15 years or some particular years of time. So for those duration of time, the satellite will experience to so many atmospheric disturbances and to say solar eclipses. All these things will influence the operation of the satellite. So at that instant of time, in order to have power supply for that particular satellite, what is needed is power is to be generated, absorbed by the sun. That means the power that is coming from the sunlight that is coming from the sun will be received by the solar panels in the satellite, and the power will be generated there, and based on that the satellite has to function. So again, solar panels are carried in additionally, so additional weight will be increasing. But the one important aspect by using solar panels here is it reduces the amount of fuel to be lifted during the time of launch to maintain the satellite in the orbit. See, if solar panels are placed and they are consuming power from the sun and generating power, so that what happens, we don't need additional fuel, since those batteries will function depending on the power generated themselves by the solar panels. So these were the important factors, and their dimensions are very, very critical. The other important thing here is 3 other factors will influence the system design, satellite system design. So what are the 3 other important elements? First one, at which frequency the satellite system is designed. At which frequency, uplink frequency, downlink frequency. Either it is used for 6x4 gigahertz, 14x11 gigahertz, or 30x20 gigahertz. At what frequency range particularly, and at what frequency links to say they are used. Second one is how the effect of the atmosphere, that is atmospheric propagation effects on the satellite, is to be taken into consideration. And lastly, which type of multiple access technique suits for our satellite communication. All these 3 factors will influence the frequency which you choose and how the satellite is supposed to function. Therefore, these 3 important elements, based on these 3 important elements, it is to define and discuss which type of frequency band we are going to choose, either 6x4, 14x11 or 30x20. See, each and every frequency linkages are having their own limitations. See, if the frequency uplink and downlink frequency increases to 30 to 20 gigahertz, as the frequency increased, what happens? The attenuation provided in this communication system will increase. So this is the problem. But whereas the 6x4 and 14x11 gigahertz frequency, when they are implemented, the satellites do not cover the entire globe. It can be implemented up to LEO orbit or to say MEO orbit only. So huge number of satellites are already there in those orbits. So traffic of the satellites will also increases. So all these things are to be taken into constraints. See, when rain comes, during the time of rain and that type of atmospheric conditions, severe experience of attenuation will be received there by the high frequency signals. To say clearly, attenuation through rain increases roughly as the square of frequency. As frequency is increasing, to the square of that one, attenuation also increases during rainy atmosphere. At the time, usage of the 30 to 20 gigahertz of frequency link suffers heavy attenuation than that of 14x11 gigahertz. So these are the things we have to take into consideration in designing satellite for a specific orbit like LEO, MEO, GEO, and for a particular applications. Depending on that, the design constraints will changes. So all these things are there. Very particularly GEO satellites are there, and they are implemented to transmit signals from satellite to the ground station. So earth station antennas will also basically, earth terminals need low gain. Omnidirectional antennas are used at the ground station. Sometimes unidirectional, directional, and omnidirectional antennas are supposed to be used in the antennas that are there in the satellite also. So for applications such as LEO and MEO satellites, sometimes they might have used different types of antennas called multiple beam antennas. So not a single antenna for a single beam application, multiple beams can be implemented here. so that the gain of that antenna system will increases. So the gain of an antenna systems that are used by multiple beams will also increases. The important thing here is the frequency reuse technique is implemented. Frequency reuse technique is implemented. So whereas for mobile satellites, terminals, natural terminals antennas, naturally small antennas are used. Low profile with low gain antennas are used for mobile satellite terminals. Likewise, for different applications, different types of antennas has been used. This picture simply represents what is saying, from ground station we transmit the signal to the satellite, and from satellite the signal comes to the ground station. For in the ground stations it may give for different applications like 1.6 gigahertz including communication to ships directly, and 1.5 gigahertz downlinks for ships, and also 4 gigahertz downlink is used for different interconnecting networks. All different types of applications can be used. Even ship with 2 meters dish antennas were also used here. Likewise, different antennas, different applications has been simply shown in that particular diagram. Now, all the communication links are designed to meet, all these things we are discussing to meet system performance. The performance of that system should increase. The performance of a system, either it is increased or increased or normal or nominal to say, that can be defined by two important elements. One is BER, bit error rate in digital systems or digital link systems, whereas in analog link systems we call it as a signal to noise ratio. These two parameters are used as a measuring elements to determine the link. One is BER, bit error rate, and next one is signal to noise ratio. So based on these things, different types of applications are used, and different types of satellites for different types of applications, for different types of frequency bands has been used here, and BER is supposed to be calculated. The moment here when we are using BER, when we are going to calculate signal to noise ratio, to a maximum, the signal to noise ratio must be greater than 6 dB for better BER. Rate. So signal to noise ratio or carrier to noise ratio should be greater than 6 dB in general for having a better performance by satellite. Generally, in digital link operations, carrier to noise ratio should be below 10 dB and must have error correction techniques. So if there are any errors that are there in the connections from transmitter to receiver, from uplink to the downlink, those corrections should be performed. Those corrections are to be performed to improve the bit error rate. Is the main objective here. So we have to improve the bit error rate, whereas in analog links it requires very large signal to noise ratio. And the improvement of large signal to noise ratio has to be performed. To perform these two activities, what we do is to calculate the carrier to noise ratio. This is important in designing the satellite communication. So designing of an uplink and downlink depends on the carrier to noise ratio in analog links, whereas bit error rates in digital link satellite communications. That's those things we have to calculate and determine. Depending on that, design will be taken place. So naturally from ground station to satellite signal goes, this is uplink, and from satellite to ground station signal comes, this is called downlink. So these two systems are there, and for that we have to calculate overall carrier to noise ratio, and that depends on both the links, uplink as well as to the downlink. On a collective note, what we have discussed right now is, from the ground station to the satellite, signal will be transmitted with one frequency. That frequency is called uplink frequency. And from the satellite, signal will be pushed down to the ground station with one frequency. That frequency link is called downlink frequency. And here, to design a satellite uplink and downlink, very first we have to understand when the signal is transmitting from ground station to space, that means to the satellite, how the attenuation is experienced by the satellite, how the signal is experiencing some attenuation, at what frequencies the signal is transmitting, either it is going at 6/4 or 14/11 or 13/20 gigahertz. And what is the carrier to noise ratio? What is the signal to noise ratio? What is the bit error rate of that one? Which type of antennas has to be chosen? For which type of applications? These frequency bands will be suited. Those design considerations ought to be taken with a detailed care by the satellite designers. This is what we understand from the introductory note. Now, let's go for the another topic, that is basic transmission theory. Basic transmission theory. In basic transmission theory, what do you mean by transmission theory? See, we the electronics and communication engineers naturally intended to design a communication system. A communication system naturally comprises of source to the destination. From source to the destination, information or communication is to be established. For that, what we do is source, transmitter, channel, and then again receiver to the destination. This is a simple block setup for establishing a communication system. So naturally at transmitter side, we have an antenna called transmitting antenna. At the receiver side, that means at the destination side, we have a receiving antenna. This from the transmitting antenna, an electromagnetic energy is produced, and through that electromagnetic energy in a common air interface, CAI, in a common air interface in free space, signal will be transmitted, electromagnetic waves will be propagated, and at the receiving end, the receiving antenna will receive the signal. So for this particular distance, the communication is established through electromagnetic waves by an antenna transmitter and an antenna receiver system. So for these particularly, maybe at the transmitting side, the transmitting antenna has transmitted power. It might be transmitting some power called P suffix T, transmitter PT power. Naturally, this PT transmitted power will be received by the receiving antenna at the receiving end, separated by a distance R, and that received power is PR. Now, depending on the aperture, effective aperture of an antenna, receiving antenna, effective aperture of the transmitting antenna, depending on the gain of the transmitting antenna, depending on the receiving antenna's gain, and also what happens, the distance between the transmitter and receiver, some power will be transmitted from the transmitter and will be received by the receiving antenna. The relation that explains the relation that gives the receiver power to the transmitted power or transmitted power to the received power relations is called basic transmission theory. Basic transmission theory. Those things we are going to now discuss here. So the calculation of power received by the earth station, from the satellite to the receiver, some signal is supposed to come, and that is going to be calculated now. How much power, how much received power, and how much transmitted power is there. Excuse me. First one is the use of flux density, and next one is the link equation. We can establish the link equation, and also by calculating the total amount of flux transmitted and the total amount of flux received at the receiving end. By making these two calculations, we can determine. Okay, now let us consider a scenario that from a transmitter, that is from an antenna, from a source. Basically, we know there are two types of antenna. Natural for calculation, we have two types of antennas. One is isotropic antenna, next one is anisotropic antenna. Isotropic antenna is an antenna which radiates uniformly in all the directions. An anisotropic antenna is an antenna which do not radiate uniformly in all the directions. So let us take a point source, that to an isotropic antenna which radiates uniformly in all the directions. Let us see, here we have one antenna, and that antenna is an isotropic antenna. This isotropic antenna radiates electromagnetic energy. It transmits electromagnetic energy. Let us assume that this transmitted electromagnetic energy having a power PT is traveling for a distance of R meters. And at this particular position, we call it as an observatory point, an observation point or far field point. So all the energy, antenna, since it is an antenna, it radiates electromagnetic energy. Naturally, antenna radiates electromagnetic energy in the form of a spherical structure, that means sphere. So this radiated energy will move up to a distance of some distance. Let us say we have taken R meters of distance. At this location, rth location, we are going to calculate the total amount of power received by the receiving antenna. So here, since it is an antenna, it is radiating electromagnetic energy. In other words, we call flux is produced from an antenna. Flux, the electromagnetic radiation per area. That is the total flux that is being produced. So this flux received at the receiving antenna is supposed to be calculated. So here we have taken some area having area of A meters square, area A having units meter square. So at a distance R, how much amount of power is being received at this area? That is what we are going to say. In other words, very simply, from a transmitting antenna, when electromagnetic energy is transmitted, it covers some area. It covers some area called beam solid angle or beam area. So that beam area here it is taken as A. Now let us see. This antenna is an isotropic antenna. To measure the amount of power that is transmitted, we have taken EIRP, electrically isolated radiated power. So electrically isolated radiated power produced from transmitting antenna, let it be PT watts. PT watts. Then for a distance of R, the amount of power is transmitted. We know that an antenna radiates electromagnetic energy in the form of a sphere, an ideal condition, and that power or the amount of flux concentrated, the amount of flux crossing the surface of a sphere with radius R. As I said just now, an antenna is there, electromagnetic flux is produced in the form of a sphere. Let us see, we have taken some area here A, and the amount of flux that crossing this area at a distance R is given as. So that flux produced F is equal to, see what is going to cross that area? The amount of electromagnetic energy produced from a transmitting antenna is going to cross. Let us think that from a transmitting antenna, the total amount of power produced is PT. And this receiving antenna naturally receives electromagnetic energy. Let us say this is PR. So this PT of power transmitted for a distance R will be received at the receiving point. So that flux we have taken as F is equal to total transmitted power PT, and it is traveling for a distance R. And since it is covering a spherical radiation pattern, the area of a sphere will be taken into consideration, and it decreases square of the distance. The flux produced at a distance R, that will be inversely proportional to the square of distance as per Coulomb's law concept. So PT divided by 4 pi R square is the flux produced. Watts per meter square. So that's what we have taken here. F is equal to PT divided by 4 pi R square, watts per meter square. What is that F? See, the flux density crossing the surface of a sphere with a radius R, and it is given as F is equal to PT divided by 4 pi R square, watts per meter square. This is, let it be the first equation. We know about this concept. Then in generally we know that the antenna radiates electromagnetic energy in all the directions, as we have considered here an isotropic antenna. But antenna's radiation pattern comprises of major lobe, minor lobe, back lobe, side lobes, and different lobes we call here. So major lobe is main, that means main beam is important since it contributes to the directivity and gain of the particular antenna. So when that is taken into consideration, the gain of an antenna is to be defined first of all. Since this is an antenna which is radiating electromagnetic energy in a particular direction, to a particular direction, maximum will be contributed. In some other directions, some average power will be contributed. In some directions, zero, null power will be contributed. So different powers in different directions are going to be taken into consideration. At that instant of time, let us define what is gain. So gain of an antenna is the ratio of power. I am defining the definition. The ratio of power per unit solid angle. The ratio of power per unit solid angle radiated in a particular direction theta to the average power radiated per unit solid angle. It is an antenna, it radiates radiation pattern in some directions, let us say in all directions, but in one particular direction this antenna radiates maximum directivity, that is maximum radiation. Now the gain of this antenna is, it is the ratio of the maximum power radiated in a particular direction, let us say theta direction, P theta maximum, to the average power radiated from this antenna, That is, gain G of theta is equal to P of theta in theta direction maximum power, or the ratio of power per unit solid angle P of theta, and average power radiated, the total power radiated for that area, 4 pi area. So P naught divided by 4 pi radians. Okay, therefore we calculated what is the gain of that particular antenna. Here gain is equal to P of theta, G of theta is equal to P of theta divided by P naught by 4 pi. I repeat the definition for gain: the ratio of power per unit solid angle radiated in a direction theta to the average power radiated by the average power radiated per unit solid angle is called the gain of that antenna. So we have defined what is the gain of this antenna. Now let us consider transmitting antenna has one gain. Similarly, receiving antenna will also has its own gain. Now let us consider that transmitting antenna is having gain GT. Receiving antenna will also has its own gain. Let us say this is G suffix R. We let assume that it is GT and next one is GR. Now in continuation to that one, let us see. The reference for the angle theta is usually taken to be the direction in which maximum power is radiated. That's what I already explained. So the theta direction is the direction in which maximum power is radiated. So that's why I define gain of an antenna is the maximum power to that of the average power. So now let us consider that for a transmitting antenna with output power PT, consider that there is no losses, that is, it is a lossless antenna. At the time, the flux density in the direction of the antenna is bore site at a distance r meters is. Now we are going to extend the power that is radiated from this antenna. That is F is equal to, we know that the total power PT, and we know already the equation is 4 pi r square, but that depends on, in a particular direction the gain is concentrated. So now gain is very important. So now include gain to that particular power of transmitting power. Therefore the flux produced at the receiving antenna, F is equal to the total amount of power radiated from a transmitting antenna included with its gain, transmitting gain. So PT ZT divided by 4 pi r square is our another equation. Now in continuation to this one, we call the product, this product PT and ZT. This product PT ZT is often called as effective isolated isotropically radiated power, EIRP. We call it as EIRP. And see, with reference to this one, if an ideal receiving antenna with an aperture area, aperture now is taken into consideration. Let us see, aperture means this is an antenna, this is the aperture of that antenna. So aperture of transmitting antenna is AET. Similarly, aperture of the receiving antenna is AER. Now total amount of power that is radiated from a transmitting antenna depends on the aperture of that antenna also, no. So therefore the receiving antenna, this receiving antenna will receive power. This receiving antenna will receive power from the transmitting antenna PT, and this transmitting antenna is now producing flux F. That flux F is supposed to be received here. That flux F is receiving here. Therefore, the received power now depends on the aperture of this receiving antenna. Therefore, PR is the product of aperture of the receiving antenna to that of the flux concentrated in this particular area. So therefore, PR is equal to F to the product of A watts. Very simple. So from transmitting antenna to receiving antenna, the power is supposed to be distributed, and that is being received at the receiving antenna, and depending on the receiving antenna's aperture. Therefore, PR, received power PR is equal to F cross A, F product of A in watts. Now, as already I mentioned here, the transmitting antenna has its effective aperture AET, receiving antenna is also having its effective aperture AER. In constraint to these parameters, we can extend the concept to efficiency. Depending on the efficiency of the transmitting antenna and depending on the efficiency of the receiving antenna's aperture efficiency, the received power will be implemented. So basically there are two types of apertures, physical aperture and next one is effective aperture. Therefore, depending on the effective aperture of a receiving antenna and transmitting antenna, the efficiency of that aperture of that particular antenna will be defined. Therefore, now when efficiency is taken into or effective aperture is taken into consideration, then the reduction in efficiency is described by using an effective aperture AE. It means, let us say this is the aperture of an antenna, transmitting antenna. Though this is the physical aperture of a transmitting antenna, all the physical aperture of this transmitting antenna do not radiate. Only some part of a aperture of this antenna may radiate. So that some part of the aperture which actively radiates is called effective aperture of this transmitting antenna. Similarly, if this is the receiving antenna, all the physical aperture of the receiving antenna may not receive all the signal. At the edges, the signal, when they fall on the edges, they reflect in other directions and that is not been captured by the receiver. So only some part of the aperture of this antenna will capture the signal. That aperture is called effective aperture. Now, depending on the physical and effective aperture of transmitting and receiving antennas, the efficiency of these antennas will be dependent. So the efficiency now may be reduced due to the uneven distribution of signal at the apertures. Therefore, the reduction in efficiency is described by using an effective aperture. Now, the effective aperture, let us say it is taken as AE. Then effective aperture of an antenna AE is efficiency or aperture efficiency neta A and product of AR, and it is product of AR, where AR is aperture of the receiving antenna, neta A is the aperture efficiency and AE is the effective aperture. Now likewise we calculate what is AE also. Now in continuation to that one, what we do is, see in this particular diagram, from a transmitting antenna which is having EIRP, that is radiated power, transmitted power will be received by the receiver. At the receiver, it will be having received power PR, and that depends on the receiving antenna with area A meter square, which has receiving gain GR, and all the incidented flux density. How much flux is incidented here? F watts per meter square is incidented, that will be received by the receiving antenna. Now let us see the total amount of power that is received. The total amount of power that is received depends on several factors: the gain of the transmitting antenna, gain of the receiving antenna, effective aperture of the transmitting antenna, effective aperture of the receiving antenna, distance between the transmitter to receiver, power transmitted, received power. Now that relation will be taken as received power PR is equal to PT, product with gain GT, effective aperture of that antenna AE, divided by 4 pi r square. Now PT GT we have already defined as EIRP. For that, effective aperture of that antenna is described and that is producted, and actually the same equation will be rewritten here. So PR is equal to PT GT AE divided by 4 pi r square is the general equation, that is the general power that is received at the receiving end when the gains are supposed to be considered. In generally, parabolic reflectors antennas are used, and the effective aperture or efficiency of the antenna is typically ranging from 50 to 75%, lower for smaller antennas and higher for large Kasigari antennas. Effective aperture is larger for large Kasigari antennas. Those concepts we mentioned. Then let us calculate the gain of that particular antenna. A fundamental relationship in antenna theory is that the gain and area of an antenna are interrelated, and how they are related is gain G is equal to 4 pi AE divided by lambda square. Since we know AE, then we can calculate G also. So gain G is equal to 4 pi AE divided by lambda square, where lambda is the wavelength at which the frequency of operation is taking place. Now the final equation, received power PR is equal to PT GT GR divided by 4 pi R square. That is 4 pi R by lambda whole square, where wavelength of that particular antenna operation is taken into consideration, and this equation is called link equation. What is that? It is link equation. So that is the link established from transmitter to that of the receiver, with gain of a transmitter and receiver, aperture of transmitter and receiver, transmitted power and received power, all those things will be taken into consideration. This is called link equation. And the term 4 pi R by lambda whole square, this 4 pi R by lambda whole square is known as loss, that is path loss. We simply represent as LP, path loss equation. So finally, the total amount of received power received is equal to PTGT is EIRP. So EIRP product with effective aperture of the antenna, that is receiving antenna gain whole divided by all the bottom term is nothing but path loss. So path loss. So finally, power received is equal to EIRP receiving antenna gain whole divided by power loss. This is the generalized equation and expression for calculating basic transmission theory. In terms of decibel quantities, can be expressed as PT transmitted power is equal to EIRP producted with gain, no, therefore plus GR, and at the bottom you will be having path loss, no, therefore we have written minus LP, decibel watts. We just transformed that equation into decibels. PT is equal to EIRP plus gain of the receiver GR minus path loss in decibel watts, where EIRP can be taken as 10 log to the base 10 of PT GT in decibel watts. Now the gain of the receiving antenna GR can be taken as 10 log to the base 10 of 4 pi AE divided by lambda. LP can be taken as 10 log to the base 10 of 4 pi R by lambda whole square. Okay, this is 20 log base 10 4 pi R by lambda. This is how we can calculate PT, GR and path loss. The above equation is an idealized case, but generally these idealized things cannot happen in practice. So naturally, from the satellite transmitter to the receiver, when the signal is passing, general thing is when the signal is passing on, it experiences to attenuation that results in losses, path loss losses, and also so many other atmospheric losses also will be incurred here, path loss, atmospheric losses. And when it comes to the receiving side, that receiving antenna should have its gain, and here also some losses will be there at the receiver, that is losses at the receiving station, and then it is given to that received power from the transmitter will be taken, and that has to be amplified by using low noise amplifier, and through low noise amplifier signal will be amplified and then retransmitted. That's how we can calculate the information transmitted. Now the relation is received power PR is equal to, now we are talking about received power PR is equal to transmitted EIRP, that is EIRP plus gain of the receiver GR minus path losses and also atmospheric losses LA, and also the transmitting losses associated with the transmitting antenna, that is LTA, and minus losses that are associated with the receiving antenna, that is LRA. That's for that only we have drawn this previous diagram. In the previous diagram, EIRP is transmitted, and that signal when it is passing on to the receiver side, it experiences to path loss, and also at the atmosphere will create some atmospheric losses, and at the aperture of the receiving antenna itself also will create some losses, and then finally given to the receiver. Therefore collectively the equation is written as PR is equal to EIRP plus GR minus LP path losses minus LA atmospheric losses minus LTA transmitter losses minus receiving antenna losses LRA in decibel watts. That's all about basic transmission theory concept. So in this concept, as I concluded, as I have established the concept in the very first beginning of this topic, from transmitter to receiver, when signal is supposed to be transmitted, antennas, particularly the transmitter and receiving antennas, aperture, gain, transmitted power, received power, distance between them are very, very critical and very important in analyzing. This is all about the basic transmission theory in satellite communication. Now let's give a small definitions, or to say points, what you have understood or what you have taken as a key takeaways from these two topics, from this satellite link design concepts in the comment section. You please drop your understanding in a single sentence or a word, or the things which we have understood from this topic in the comment section. We just have an interaction with you through the YouTube comment section. If you have any questions also, you kindly drop your questions there and I will answer to those questions also. Next topic is system noise temperature and G/T ratio. A very, very important and interesting topic now. See, once we established link between transmitter to receiver, now the signal, when it is propagating from one point to another point, from this point to this point, it will experience to the atmosphere, free space here, and also in this atmosphere, temperature is a very critical point. This temperature will influence the propagation. Naturally will influence the propagation. Then how this will influence the propagation? Naturally, see, we are sending some signal with some carrier power, and that will be received as a carrier at receiver CR and carrier at transmitter. In between, all the factors, many other factors, atmospheric losses, path losses, temperature, everything, many other factors will create important element called attenuation to the wave that is propagated. When attenuation is experienced here, the performance of the system basically depends at the receiving side by carrier to noise ratio. Now here this carrier to noise ratio is very, very important, and naturally this should be maximum or larger, to say. Large carrier to noise ratio is to be established in any communication system. So carrier should be very high, noise should be very minimum. So to do so, engineers plays a vital role in designing. So how we have to design that carrier and noise is a critical factor here, and we are going to define those things in this particular topic. Let's see. So this is little derivative part, or to say formula based, and topic has to understand here as per the formula based. If you are ready with your some notes and paper and pen, it will be better to write so that you can get a continuity of understanding. Else, if any point misses here, then you may not get a continuity. So better, if it is possible, you take your notebook and write the things. So here, let us see noise temperature. See, noise is established. See, main important factor, main important point what we understood here is, from transmitter to receiver, when information, or to say when signal is propagating, noise is an important factor. This noise, when it is added here, and that noise will disturb the performance of the system, and how this performance is now affected, that is important. So, and that is what we are going to calculate here accordingly. So noise temperature, it is a useful parameter or a useful concept in communication at the receiver end. At the receiver end, it provides how much thermal noise is generated. How much thermal noise? Which type of noise? Basically, thermal noise. How much thermal noise is generated here? Noise that is produced in the different components at the receiver. That is going to be calculated here. And naturally, we are talking about satellite communications. Basically, the satellite communications operates at gigahertz called microwave frequencies. So at microwave frequencies, to say all the different components in that receiver, called a black body of that receiver, will have its noise power. So all the components at the receiver will generate some power, that is noise power. So that noise power can be calculated as in the formula called, see, as in the previous topic we said, here we are having receiving power. Yes, this receiver power is composition, it comprising of noise also, no? So how much is this noise power? That noise power will be taken as Pn is equal to KTPBN. This is the relation. This noise power Pn is equal to KTP and Bn, where K is the Boltzmann constant and its value is 1.39 into 10 to the power of 23 joules per Kelvin. And whereas Tp is physical temperature of that components, to say clearly. So physical temperature of the source. Bn is noise bandwidth. Bn is noise bandwidth. So this product gives you the power of noise, or simply to say noise power. Whereas this product KTP is noise power spectral density. We call it as noise power spectral density. Noise power spectral density. This product KTP is called as noise power spectral density. So simple understanding is, when a signal, an electromagnetic wave is propagating from transmitter to receiver, at the receiving end the received power will be there, and that received power received here by the receiving components during the process of propagation and during the process of signal generation, and at the receiving side noise is also associated. And in generally, when we are talking about designing of a receiver, the power, that is the total amount of power, the to noise power, is estimated with a relation Pn is equal to KTP into Bn, where Bn is the bandwidth of the noise, Tp is the physical temperature of the source, and is Pn. Now let us take another important. This is the first conclusion. There is cut one, first scene, or first understanding of what is the noise power. And in continuation to this one, let us see a clear picture is there here. In a satellite communication from a transmitting source, generally an electromagnetic signal that is transmitting towards destination, generally it produces weak signals. As it is associated for longer distances, no, that means satellite communications are basically intended for longer distance communications. When signal is to transmit for longer distances, at each and every interval of propagation and at each and every interval of signal generation at transmitter and receiver, noise is associated, and this noise level will decrease the performance of that system. Therefore, noise level should be reduced. So at the destination side, the noise level should be reduced. That is what we need to understand. So at receiver, carrier should be maximum, noise level should be minimum, carrier to noise ratio should be maximum. So that is what to happen. So to perform that one, what is required is intermediate frequency amplifier stage is needed, and also the bandwidth at the receiver we have to set. This is the prescribed amount of bandwidth that is received by the receiver, and this intermediate amplifier amplifier stage will allow the signal to amplify, and only at the band pass filter, that means at the bandwidth when we are restricting there, only the required signal is allowed and the other signal will be eliminated. That thing will be done. So if we allow only the required signal to be allowed, itself is eliminating the noise, to say clearly. So noise will be reduced here. That is an important factor. So naturally the noise temperature ranges from 30K to 200K, 30 Kelvin to 200 Kelvin, and that can be achieved without any physical cooling if The amplifier that is associated to say, let me make you clarity. From transmitter to receiver, when electromagnetic energy is radiating, when electromagnetic signal is radiating or propagating, to say, in between we use amplifiers. In between we use amplifiers, intermediate frequency amplifiers to amplify the signal. Those amplifiers which are used here, if they are prepared with or manufactured with gallium arsenate FET amplifiers, gallium arsenate FET amplifiers are used, then their noise temperatures will be achieved or to be ranging from 30K to 200K. In generally, the noise temperature increases as frequency increases. So noise temperature is also increases as frequency increases. So the performance of this system, particularly at the receiving side, if you want a desirable or a reasonable amount of performance at the receiving side that can be achieved, we have to find how much amount of thermal power or thermal noise power is there in this particular case. So to say, in generally we use modulator at transmitter and demodulator at receiver side. At this demodulating section, the received power will be there and noise power also there, and we have to estimate how much thermal noise power is generated here. So if we estimate this one, then we can finally easily find out what is the total noise that is associated in this particular system. So this can be done by finding system noise temperature. So for this entire system, what is the temperature? So system temperature. So here now our concept is to estimate the total system temperature is to estimate. So overall end-to-end gain of the receiver is important. Gain of the receiver, bandwidth at which the frequency, bandwidth at which the system is functioning, everything is associated. So with all these factors, we are going to calculate the total noise power at the demodulator input. So at this demodulator input, we are going to find the total noise power, and that total noise power at the demodulator input side is given as Pn naught is equal to noise at the output side. Pn naught is equal to Kt. Tp is actually, in the previous case we have taken Tp, physical temperature, but now we are taking for the entire system. Therefore we take Kts, bandwidth of that one Bn, and the receiver's gain. Now receiver's gain will also have influence on the temperature of that particular system. Therefore Pn naught is equal to Kts Bn, that means bandwidth, Grx. Receiver, Rx means receiver in watts. This is the important equation which we consider. Then the noise power to the input of the receiver is, Pn is equal to Kts Bn in watts, general expression. So from transmitter to receiver, when a signal is propagating, included with gain of the receiver, at the receiver we receive two types of, since it is an antenna radiating signals, we receive two types of signals, that means major beam, minor beam, as well as backside lobes also. So all these will be there. Those are all the side beams which are there in that one are the losses to say, and therefore amplifier stage should be used at the receiver. So amplification has to do, and also since we are associated with satellite communication, transmitted with uplink, downlink, so frequency conversion has to be taken place. So uplink to downlink frequency conversion has to perform, a demodulator frequency conversion, down conversion has to be taken place. So here at the receiving end, receiving amplification and frequency conversion will take place. So the carrier to noise ratio at the receiver end, that to the demodulator end is given as C/N, carrier to noise ratio. The carrier means transmitted signal received at the receiver side. So that is PR associated with the gain of that receiver. So PR Grx is the carrier. Now the total system temperature is the important factor. That is noise actually. So Kts bandwidth and receiver. This is just equation, previous equation we have taken. So PR Grx divided by Kts Bn Grx. Simply we write it as PR. This Grx will cancel each other. PR divided by Kts Bn, bandwidth of the noise, is the equation. So now this entire system temperature we have to calculate. To calculate this entire system temperature, noise temperature. It follows in 3 different stages. What is that? Let us see this diagram. Let us see this diagram, then I will explain here. So signal from satellite will be received by the receiving antenna. That signal immediately, that means the received power PR, that will immediately pass on to the low noise amplifiers. So this low noise amplifier is a part of receiving section. Therefore here the gain of the receiver is important factor, GRF. That signal immediately passes to band pass filter, and from band pass filter, that means it allows only the prescribed frequencies. So band pass filter, noise eliminates, some sort of noise will be reduced here itself only, then passes to the mixer with local oscillator for down conversion. Here the gain of the mixer is also an important factor, GM. Then band pass filter again, followed to the intermediate frequency, that is amplifier, intermediate frequency amplifier, then IF output will be there. This is a simplified earth station receiver band pass filter concept. Okay, now with reference to this, let us analyze the concept. So from that figure, that is a form used for radio receivers, generally our receiving section, satellite communications receivers, with expectations, or to say exceptions, known as what is there in here. That receiver we call it as simply superhet, or we call it as super heterodyne receiver. Superhet or super heterodyne receiver. Now this super heterodyne receiver comprises of 3 sections to say. One is front end section, intermediate frequency amplifier section, and demodulator and baseband section. Likewise 3 sections will be there. In front end section, what happens means the RF signal that is directly coming from satellite will have to amplify. So RF amplifier is there, and also mixer will be there. Associated with mixer, it has a local oscillator. This section is front end section. And the second section is IF amplifier stage section, where IF amplifiers are there. Automatically filters are also there. Since it is amplified, only required signal needs to be passed, means filters are also there. And finally the demodulator section, which receives the baseband signal. Likewise 3 sections are there. In RF amplifier, in that too in satellite communications, as low as noise produced should be done. That means noise should be produced to a very low extent, such that the communication should be much better. Therefore we use low noise amplifiers. As I have shown in the next diagram, low noise amplifiers are used here to reduce the noise, or to say very low noise. Then from RF to IF conversion should take place. Therefore RF to IF conversion will take place here, where signals can be amplified, filtered accurately, and will be received. That is there in this diagram again. Okay, later. In some cases, earth station receivers uses double super heterodyne. Called double super heterodyne configuration is also used. Just now we described is a single super heterodyne. There are sometimes we use double super heterodyne sections, which is as shown in this particular figure. Satellite signal gone to the low noise amplifier, band pass filter, mixer, band pass filter, first intermediate frequency amplification. From first intermediate frequency amplification passes to band pass filter, next mixer with local oscillator, second local oscillator is used here, band pass filter and amplifier, second IF amplifiers are there, then to the demodulator section. Likewise 2 stages intermediate frequency conversion will takes place. So this is, let us see, this is explained as in this diagram. What we have noticed is that has 2 stages of frequency conversion. Very first, the RF signal will be received by the receiving antenna. In the receiving antenna, the front end converts the IF signal at a range of 900 to 1400 megahertz. At what range? 900 to 1400 megahertz. With a bandwidth at C band or KU band that is implemented here. And that RF amplifier has high gain antennas, and a mixer is followed by a stage, mixer stage of IF amplification. After IF amplification, it go for mixer, and this section of receiver is called low noise block converter, LNB, low noise block converter. Okay. After conversion of this one, what we do is this 900 to 1400 mega signal is sent over a coaxial cable to the next level, that is down converter with a tunable local oscillator, and in this tunable local oscillator the signal is converted and it is selected and it is retransmitted to the selected from the respective transponders for second IF intermediate stage. And at the second IF the signal is now down converted with a bandwidth that is particularly matched. So simple. What we performed is two stages of conversion will be taken place. So two amplifier levels and two IF amplifier levels will be there. So in order to analyze this noise, let us see this diagram. So very simple diagram. The temperature at input is given at the receiving RF temperature that is given for the receiver. That is, gain of the receiver is important thing. So noiseless RF amplifier. Here some temperature will be included here. That is given to the mixer. So temperature at the mixer stage will be added. From that gain, noiseless mixer that is given to noiseless IF amplifier at each and every stage. It means to say at RF stage, at IF stage, at mixer level stage, IF amplifier stage, mixer down conversion stage, and also at RF level stage. At each and every stage, intermediate stages, temperature will be added, noise temperatures will be added. So TRF, TM, TIF are the important factors. All are associated to total power of noise, that is PM, in simple words to say. So in order to analyze this one, what we have to do is, noise devices are to be analyzed. The total noise power at the output of IF amplifier of the receiver is, this is IF amplifier stage. At this IF amplifier stage, the total noise we are going to calculate. That noise level is Pn is equal to, see, let me explain this equation. Pn is equal to GIF, intermediate frequency gain, KTIF-BN plus GM KTBM-BN plus GIF GM GRF KBN TRF plus TIN. All the parameters, or to say all the factors that are associated here, TRF, TM, TIF, are summarized here and taken as an equation. Pn is equal to GIF K TIF BN plus next intermediate frequency with mixer and its bandwidth, next intermediate frequency, mixer with RF, and the total RF plus intermediate frequency. So all these collectively will be taken, where GM is gain of the mixer, GIF is IF amplifier gain, TIN is noise temperature of the antenna. Likewise, we place the equations. This is about that equations. And for today's session, we just stop here. As the time passing more, we stop here. We discussed about three important topics: signal to noise and G/T ratio concept, basic transmission theory concept, and introduction to a general establishment of satellite uplink and downlink. The next topics in this week, we do go for live session or may give some video lectures, and in this week we have to face two assignments. One assignment is certificate of appreciation assignment. Next one is an assignment which gives you certification of merit certificate. Likewise, two assignments will be provided for you. Get ready. I have already shared you the PowerPoint presentation of all the previous talks and video lectures, and their YouTube links also have shared to you. Please go through those links, understand the topics, try to understand and make a lot of discussion, so that, see, happy learning is the concept. That's why all this big setup and contributing our time and knowledge is being shared to students, faculty, researchers, and all those things in order to explore the electronics and communication engineering. See, wherever you go, communication is an important parameter. That too, satellite plays a vital role. So we feel so happy and proud to understand, learn about satellite communications. So I feel so happy to share the knowledge what I do have regarding satellite communications to the participants, and thank you very much. Happy learning. Thank you. If you find any questions, kindly drop the questions in our WhatsApp group. Also drop the questions in the comment section. At the later stage, we will have a direct one-to-one interaction through Google Meet or Zoom or somewhere else, and we will have a detailed discussion on the topics. Thank you.